Hello and welcome back. Today we want to talk about some examples using the central limit theorem and the sampling distribution of sample means. So I'm going to start with kind of an ordinary problem. Let's suppose that we have an elevator and it's got a load limit of 2,300 pounds. Now, in the usual course of things, when people get on an elevator, you get young people, old people, infants, toddlers, sub-teens, elderly. But sometimes you might find that you've got, let's just say, a lot of males, adult males, and maybe 12 adult males get on this elevator. So 12 adult males get on. Our first question is, what's the probability that this elevator is now overloaded with 12 adult males? Well, we know some things about this. We know that W is equal to the weight, this is a random variable W, weight of adult male, and we know that W is normally distributed with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. So we know that from reading the pages of our textbook. That's a given. We could use a data set in the back of the book where we've measured the weights of 300 men and come up with estimates of the mean and standard deviation. They'd be very close to those that are given. This is about the population. Not a sample now. That's the probability distribution for weights in the population. But we want to know if this elevator is overloaded. So how would we go about that? Let's put on our thinking caps here. We've got a load limit of 2,300 pounds, and we just put 12 men on the elevator, and so that would mean that 2,300 divided by 12 is 191.67. If the men have an average weight that exceeds 191.67, then the elevator is going to be overloaded. See, if the average weight was 191.67, then the total weight would be 12 times that. In fact, whatever the average is, multiply it by 12, and that would be the total weight of the 12 men. So it turns out then that the probability of being overloaded is equal to the probability that the average weight of this group of 12 exceeds 191.67. That the average weight exceeds 191.67. Now, how would we figure that out? So we want the probability that W bar is greater than 191.67. Now, if I know the distribution of a random variable, like say W bar, then I can calculate any probability associated with that random variable. If I don't know the distribution, I can't calculate any probability at all. But in this case, we're very fortunate because we know from the central limit theorem that W bar is, okay, now what does it say about the shape? The central limit theorem says W bar is normal under two conditions. If W itself is normal, And we're in luck because the problem says that W is normal. There is a second condition. We don't need it in this problem because we've got W itself as normal, which implies that W bar is normal. Central limit theorem. But if we didn't know that W was normal, but if our sample size was greater than 30, W bar would still be normal. Now, our sample size is not greater than 30, it's 12, but that hardly matters to us because we have W normal, and the central limit theorem says, oh, if W is normal, then W bar is normal. So W bar is normal. Now, the central limit theorem tells us two other important pieces of information, pieces that without which we cannot go ahead. So the central limit theorem further says the mean of W bar is equal to the mean of W, and that we see from right up here from the given information is 182.9. And we get one third thing that we really need. I don't know why that keeps happening. We get one third thing that we really need, and that is we need to know what the standard deviation of W bar is. And the central limit theorem tells us that it's going to be 40.8, which is the standard distribution, standard deviation of W, divided by the square root of the sample size, so that's by the square root of 12. And with your calculator, you will calculate that to be 11.78. 11.78, like that. All right, so to summarize, W bar is normal 182.9, 11.78. And what we want to do, this is really a sketchy sketch, but we want, now let's see what we've got here. Just for scale, right under the peaky part is 182.9. And so the 191.76 would be up here somewhere. 191. I think I said 76, but it's really 67. And this is the probability we seek right there. So we're going to go to Minitab and we're going to get that. What we're going to have to remember is the boundary is 191.67, the mean is 182.9, the standard deviation is 11.78. So I think I can remember all that. In fact, I know I can't, but I've got it written down on a piece of paper. So let's get Minitab up. That's probably good enough. So I'm going to go to Graph, Probability Distribution Plot, and there's a couple things I've got to feed in here. I want to view the probability, so I'll take that fourth icon and say OK. And now, what is my distribution? It's normal. What's the mean of my distribution? Well, it's 182.9. Now that's already typed in because I did this problem a few minutes ago. So 182.9 is still correct. What's the standard deviation? We calculated that to be 11.78 with the help of the central limit theorem is how we figured that out. Now, what shaded area do we want to know about? Well, remember from our little sketch, it's the upper tail or the right tail, and it's defined by an x value. So it's not defined by probability, but by an x value, a value on the horizontal axis, and that value was 191.67. So we're going to say OK, and this is the picture we get. And that looks like the picture we sketched back on the graphics tablet. The boundary is 191.67, and the area to the right is 0.2283, and that's the probability that W bar will exceed this value right here. But what would that mean? Exceeding this value, where did I write it? Exceeding this value here, exceeding this value here, means the elevator is overloaded. So we've just found from Minitab, we've found this area is 0.2283, 0.2283, and all of this implies there's about a 23% probability that the elevator is overloaded. So if the people that get on are not the usual mix, but are all adult males, and if there's 12 of them that get on, then there's a 23% that the elevator is overloaded. So that is kind of a typical problem, and it's a problem that's actually used for calculating loads on elevators and boats and airplanes and other conveyances maybe that I'm not thinking about right now. All right, so I don't see where I had picked out another problem to work. That surprises me, but let's have a short video. I think this will be the shortest one we've made this semester. So look for more. That'll do for today, though. Thank you very much for being here.